leading international researcher venues, establishing himself as an authority in advanced antenna and intelligent surface technologies for 6G. We are honored to invite Dr. Jobin Francis to deliver an online session on massive MIMO and RIS, key technologies for 6G cellular systems, at our faculty development program on advanced communication systems, shaping next generation network. We warmly welcome you, sir. Welcome to the event.
My screen is visible, right?
Yes, sir. It is visible.
Yeah.
Yes, sir.
Okay. So thank you for the kind introduction and also for inviting me to this faculty development program. So it's indeed a pleasure to be here. Now, coming to this talk, the idea is to give you a glimpse of what this next generation of cellular networks might be. All of you would be familiar with 5G. That is the fifth generation of communication technology that is already there in all of our mobiles. And just a peek into what that next generation might be and some of the communication technologies that are going to enable the 6G networks. Okay. All right. Okay. So coming to the outline of the talk, first I would try to motivate why a 6G network is needed, and then we will get into the reasons for or the enabling technologies. So the obvious reason for a new generation of network is always the high demand for more data. Right. So what I've plotted here is the mobile data traffic in exabytes per month all over the world, right? Looking at from 2018, that is roughly when 5G was deployed, to present, right? That is Q3, very recently till the end of 2025, right? So you can see sort of an exponential sort of growth in the data traffic over the network, right? And this is not slowing down, right? You see that there's a consistent growth here, and that is what is shown in this bar diagram. And in addition, you also have this a solid line here, which is showing the year-on-year growth, right? So as you can see, this every year the growth in the data rate that is coming down, which means we are sort of stabilizing, right? That is the every year you are sort of now roughly growing, the traffic is growing at some 20%, right? So there was a jump somewhere around 2018, 2019 period. That is because the first 5G networks were deployed that time. And that time there was a lot of sudden surge in the consumption of data, but now the network has sort of stabilized and the traffic is settling at around 20% growth per year, right? And if you look at the projection for the years ahead, the trend is expected to continue, right? So if you this is also coming from an Ericsson, which is a telecom equipment manufacturer, a leading manufacturer, and their projection for the coming years till 2031 is showing again a consistent growth, right? And it is this trend of data is requirement for data is expected to continue. And in addition, bulk of this data would be supported over 5G or the next generation of networks, right? So this legacy 2G, 3G, 4G networks are gradually being shut down around the world. And you can see that the fraction of traffic carried by those legacy networks would be reduced, and more of this 5G and beyond networks would be carrying bulk of the data. And this expected growth is going to be driven by AI. Now there is a widespread adoption of AI. You can see AI everywhere. Everyone is using ChatGPT and large language models. Training and even inference of such models require a lot of communication, right? And also you expect to see smart glasses with the AR, VR capabilities in the near future. In addition, you also have the consistent multimedia consumption with the high quality video and audio streaming, right? Also online gaming is also going to be there. And in addition, there's IoT is there with the billions of smart devices around, right? All of this is going to push this growth for traffic or growth in traffic. Okay, now also looking at the region-wise growth, you can also see that um, the growth is going to be strong around the Asia Pacific region, right? So India, if you see this projected growth, it's the monthly consumption is somewhere around 30 GB per month now, which is going to go up to possibly um, 60 or so, right, by 2030, right? So um, the consumption of data in India is well above the global average, which is shown in this dotted line here, which is again due to many reasons. We are our basically the data is very cheap in India, very affordable service plans. Also, we spend a lot of time consuming multimedia content, right? So yeah, I think there are several reasons why this growth is expected to continue. Again, our smartphones are getting more capable, so you can basically view HD TV content or live stream matches, right? And the data plans, like I said, is very affordable. And also the quality of the video that is being streamed is also becoming better, right? And altogether, the better network allows for better quality of content to be transferred, and therefore more data is being transferred, right? So this is the obvious reason why we need a better cellular network, right? But does it alone warrant a 6G network, right? So can we just work with an enhanced version of 5G? And in fact, the more more important reason why we need a new generation of network, not just an enhanced 5G, is the sort of new applications that we envisage this network to support, right? So all of these are some envisioned technologies. One is digital twin, where you have a digital replica of the real world. So this is going to be again based on real-time inputs as well as a lot of AI, right? You expect to see intelligent transportation systems with autonomous cars, which require ultra reliable, low latency communication. So it will be frequently sending updates both to the server as to nearby vehicles. So that communication has to be very accurate as well as very low latency communication. Again, data intensive AR, VR headsets are going to be around, and then that also going to require a very precise data intensive at the same time very low latency, right? Then you expect to have a lot of robots. I mean, in fact, humanoids are coming up in a big way, right? So if you want to have some real-time control of these robots and robotic systems in an industry environment, for example, then again, you need very high precise controls, right? So drones are going to be there. There are going to be swarms of drones, which needs, again, connectivity over large distances, which means the communication technology for enabling such long distance communication has to be cellular, right? And then some futuristic applications like probably remote healthcare, such as remote surgery. All of this means, again, a very reliable network, right? So in short, these sort of futuristic applications, the requirements are well beyond what a 5G network can support, right? This has to be natively support AI, high data rate. The network has to be around everywhere, right? The drones cannot suddenly lose control because it's far away from a cell tower, right? So you cannot afford that. And also these networks also needs to be secure, given the sort of security concerns, privacy and security concerns all over the world. Okay, so that brings us to the capabilities that we demand from a new generation of network, right? So this also it's also instructive to look at it in the context of what has been there in the network and what is required going forward, right? So the first generation of cellular networks to fourth generation of cellular networks was just about connectivity, right? You just wanted to make a phone call or access some internet uh, through your mobile phone, right? So that was 1G to 3G was mostly about just voice calls, right? 4G with LTE, we started moving into more of this mobile broadband where you started accessing the internet through your phones. And with 5G, you also, in addition to this better connectivity, you also have some computing capability, which means that some of the compute intensive tasks are now getting offloaded to some server remotely located, right? So some edge computing has also come in. So that is the additional capability that 5G has given us. But going forward, the sort of requirements are going to be much larger, like I just showed in a few example applications. And there, in addition to this connectivity and computing, you also need precise sensing, right? Your network needs to function as a sensor. It should be able to localize, sense the presence of a target, and such requirements. On top of that, it has to natively support intelligent devices, and also the network itself has to be intelligent, right? So it should be able to adapt itself rather than the sort of the networks that we had in the earlier generations, right? So all of these new capabilities warrant the need for a new generation of a cellular network, right? Than just enhancing what is already there. Okay, right? So a good analogy to make here is the transportation network, right? So you can always imagine that building a communication network that is a cellular network is analogous to building a transportation road network, right? So you one thing you can always do is you can enhance the existing highway, right? So that is sort of like enhancing the 5G to maybe a 5G advanced, right? But then the sort of network or the road network that you need for future is well beyond just a few more lanes of highway, right? So it's not, wide roads are not just enough, right? Your future intelligent transportation network might have autonomous cars, some bullet trains, and many other modes of transport, right? And all of this needs to be highly coordinated with minimal human intervention, which means that your whole transportation network has to be overhauled and cannot just be a expansion of the existing highways, right? So this is the analogous thing that is there for 5G to 6G, where you expect to see a paradigm shift in the network itself. Okay, so just to highlight this analogy, you can always think of these highways as the communication capability, and some smart sensors you might have, like your AI cameras on the road, can be sort of seen as an integrated sensing capability, which is expected to be a feature of 5G, 6G. And in addition, a lot of the command controls would be centralized and might be handled by AI. And there might be other modes of communication, like in 6G, it's not just going to be cell towers. There's also going to be satellite communications and possibly some aerial network, which could be your UAVs acting as cell towers, right? And a lot of autonomous vehicles could be around, which is basically machines communicating with machines rather than machines or humans communicating with each other, right? So you can draw a lot of parallel between what a cellular network is to a road network. Okay, so with that requirements in place, right? So the International Telecommunication Union, which is the United Nations body that actually works on this cellular network, standardization of the cellular networks, they published a vision document in 2021, right? So what would be that telecommunication technology for 2030, right? What is that vision for such a network? Now, if you see this vision, this is a hexagon here, right? So these are the sort of capabilities that you want for the network in 2030. And inside there is a triangle here, and this was the vision for 5G. That was the network for 2020. All right. So you can see that from a network which is capable of supporting high data rate, that is EMBB, to many devices, to some high reliability URLLC, right? So your whole network requirements has expanded into 6 vertices now, right? You still need high data rate communication, that is immersive communication. You want to have integrated AI. Again, high reliable, low latency communication needs to be there. In addition, you want connectivity everywhere, right? So you don't want that suddenly your cell phone connection lost because you move to the basement of your room or somewhere else, right? So maybe to some remote location you go and suddenly you don't get cell coverage anymore, right? You don't want that. You want ubiquitous connectivity. Also support for IoT and integrated sensing and communication. So what are these 3 points highlighted in blue are sort of like the new requirements that we need or we envisage for the 6G network, right? But the green ones are sort of like the enhancements of existing capabilities, right? So we want integrated sensing and communication, that is ISAC, AI support, and ubiquitous connectivity. And ubiquitous connectivity is going to be largely provided by non-terrestrial networks such as satellite, right? Now, all of these new network capabilities are going to lead to some societal impact, be it in terms of sustainability, connecting the unconnected, right? You want to avoid or reduce the digital divide, right? Also, security, privacy, and resilience of these networks are highly important. At the same time, natively AI, right? Intelligent networks. Okay. So this network vision can be translated into following, right? So you on the top, you have some societal impact that you hope to get by having a new cellular network, right? And this societal impact, like we saw in the outer circle here, right, translates into daily life of users, right? So see that for these new cellular networks, the users are not just people, right? This could be machines, right? Robots talking to each other. This could be enterprises. This could be private communities having a cellular network of their own, right? And all these users have different usage scenarios, what they use these networks for. And underneath that, you require a lot of communication technologies that needs to come up to enable these new applications and usage scenarios, right? So for an engineer, all of these goals translates to some key performance indicators, that is what should be the data rate, what should be the delay, how much delay variation, what is the coverage of the network, and so on, right? So this is what a communication engineer is concerned about, right? So in trying to design a new network, right? So what are these target numbers? Okay, so I'm just showing some indicative. Okay, so I'm just showing some indicative numbers here, right? So, but the absolute numbers are not very important, but all you have to see here is that this requirement is going to be 10x or more higher than what is existing with a 5G network, right? So your network requirements are going to be so much higher compared to what is already possible in a 5G, right? For example, the data rate, the peak data rate that you might get to see would be order of Gbps to tens of Gbps, right? So that's like a factor of 10 improvement, right? But the other important point is that you also want some kind of centimeter level positioning accuracy. So the network should be able to locate you to some centimeter level accuracy, right? So in addition, you also have some energy efficiency, which is like the sustainability aspect, right? So how much energy are you spending in setting up the network? Also, cost is a big consideration, right? Because the infrastructure deployment is a very costly thing for network operators, and how to bring about cost network, right? Low cost, both in terms of network deployment as well as operation and management. Okay. Okay, so with all of that, we have a lot of targets to meet, right? So these are very stringent numbers, right? So then let's get back to some communication and see how some of or how these can be enabled, right? So at the base of everything, we have the Shannon capacity result, right? So this is the famous information theory result by Claude Shannon, who told that the rate at which you can transfer bits to any device is fundamentally limited by this expression here, right? So the setup is the following. So imagine that you have a cell tower and it is sending data to your mobile phone here. And how this does is that the cell tower takes this stream of bits, converts it into some RF signal, radio frequency signal, which is then radiated using some antennas. And part of that reaches your mobile phone, and which is a noisy, distorted version of what was sent by the base station or the cell tower. And from that, the mobile phone tries to recover the bit sequences, right? So in doing so, there is a rate at which these bits are being sent per second, and that is the capacity. And the capacity is going to be given by this bandwidth times number of layers times logarithm of some signal to interference plus noise ratio, right? So this is the fundamental result from Claude Shannon, right? And you cannot beat this number, right? So this is a fundamental limitation of the system that we have, right? So which means when we try to come up with a new network with a higher data rate or throughput, your goal is to somehow play with these quantities in this expression and then improve the network performance, right? So again, just to give an analogy here, the bandwidth is what is the Jio or the Airtels procure by paying huge amount of money, right? And that is the license to transmit over a given frequency over a given bandwidth, right? And this can always be related to something like the width of the road. Again, I'm drawing a parallel with the road network, right? So you can always think of this capacity, that is bits per second, as the number of vehicles per second or on a road network, right? Now, if you increase the width of the road, right, you can see that many vehicles can go in parallel, and thereby immediately the vehicles per second number goes up, right? So as you widen the road, the transfer of this data or vehicles in this analogy increases, right? Now the SINR, that is sort of like the signal quality, right? The coverage that you see on your mobile phone, right? That can be related to the quality of the roads, right? If you have a road with a lot of potholes and if the weather is not conducive, right, even though you have a wide road, you may not be able to drive very fast, right? So therefore, the quality of the road is somehow the analogous to the signal quality that you get at on your mobile phone, right? And the spatial layers, I'll come back to this point later, right, is somehow kind of like if you can create multiple lanes on the same road, right, parallel tracks, right, then again the vehicles can travel in parallel and your data rate goes up, right? So that is the sort of the physical intuition of how these bits are getting transferred over a wireless network, right? So bandwidth means you basically increase the width of the road. Number of layers is sort of like the parallel tracks you can have, and SINR is sort of like the quality of the link that is here, right? It's sort of like the road quality in the analogy. Okay, right? So therefore, the network operator can try and procure more spectrum, right, to increase the available bandwidth for communication, right? Now, fundamentally there are two issues with that. One, bandwidth is limited, right? So in any of this cellular communication technology bandwidth, right, the spectrum is a very scarce commodity. And it's very expensive, right? You hear that lakhs of crores are being spent in acquiring the license to transmit on a spectrum, right? So therefore, this bandwidth is scarce and expensive. So therefore, getting more bandwidth may not be cost effective also at the first place, bandwidth may not even be available, right? Okay, so that is also why there have been discussions of moving to higher frequency band like millimeter wave or terahertz frequency band, but those have associated issues there. Okay. Now the second option is to improve the link quality, that is the signal to interference plus noise ratio. That means you somehow get a better signal from the cell tower, right? The obvious option is somehow you reduce the distance between your cell phone and your cell tower. Possibly, if you are closer to the cell tower, you will anyway get a strong signal. But the other option would be that you bring the cell towers, that is base stations, closer to the mobile phones, right? So which that means is that you deploy more number of base stations to allow for this, right? So you have a denser deployment of base stations. The other option is what is called a beamforming, which is what is going to be facilitated by multiple antennas, that is MIMO, and I'll discuss that in detail in the coming slides. And also the another MIMO feature is what is the number of layers that I mentioned about, that is spatial multiplexing, right? So the data rate requirements of the next generation is going to be highly supported by the beamforming and spatial multiplexing capabilities of a MIMO system, right? Now, MIMO stands for multiple input, multiple output. And what that just means is that your transmitter, which is the cell tower in this case, is going to be equipped with multiple antennas. Okay. Okay, so let's try and understand what happens when you have more than one antenna at the transmitter. So if there's just one antenna and it is generating a wavefront, right? So when you excite it with an RF signal, it radiates electromagnetic radiation, right? And that propagates as shown here, right? You can imagine that is a point source and it is having some isotropic radiation pattern, which is generating some kind of wavefront as shown here, right? Now, if you bring in another antenna and feed it, excite it with the same signal, right? What happens is the following. So there will be two wavefronts, one from each antenna, and they start interfering with each other, right? And these points at which they interfere or they meet each other, right? That is where I have drawn this line here. And that are the points where these wavefronts interfere in phase, right? So therefore, they have the same phase along this line, and there is going to be constructive interference. And at other locations, there could be destructive interference, right? Now, what that means is that due to constructive interference, there's going to be stronger signal along this line that I've drawn here, that is the broadside direction of the antenna. Therefore, these two elements here, you end up with a energy distribution that is more pointed in this line that I've drawn here, right? That is, which means there is a radiation pattern now for this array of antennas, right? Now, that alone is not sufficient because you may not always want this energy to be directed in this perpendicular direction. You might want this to happen in maybe another direction, right? You might want to steer the beam to some other angle, not just this perpendicular direction or this broadside direction here, right? And the simplest way to do that is the following. You, instead of sending the same signal to the two antenna elements, you send them signals with a slight delay, right? So the first antenna is excited with the original signal, but the second antenna is fed a signal that is slightly delayed, right? Because of which you can now see that the points at which these say similar colors touch, right, that is slightly slanted, and therefore the direction in which the constructive interference occurs is also different now, right? So in effect, you sort of manage to steer the beam from broadside direction to an angle of interest, right? So by adjusting the delays of this signal to different elements, you can steer the beam to the direction of interest, okay? So which means that if you have a cell phone here, you can have some 4 antenna elements and create a beam, which beam here means just a focused energy in the direction of the cell phone here, right? Now, suppose you have 2 cell phones, right? And you want to serve them simultaneously, right? What you can do is the following. Instead of sending one big beam directed to only one user, you generate two different beams. The procedure is exactly the same. You just have to individually generate two smaller beams and then add together, and that generates signals meant for two different mobile phones, right? So you can keep increasing this. If you have more number of mobile phone users, you can keep generating smaller beams, but each pointed to the corresponding user, right? So these are exactly the beamforming and spatial multiplexing capabilities of multiple antennas. See that all of this was possible because we had more than one antenna in our transmitter, right? So using this array of antennas, you can either create a single large beam to a user, that is beamforming, or you can create multiple smaller beams to multiple users, that is spatial multiplexing, right? So spatially, you are sending different signals without any interference to each other, right? That is, you are able to multiplex different signals, and that multiplexing is happening in the spatial domain, hence the name spatial multiplexing, right? So these core technologies are going to be the enablers for 6G data rate requirements. Okay. So, and also the number of beams that you can generate is fundamentally limited by the number of antennas and some characteristic of the wireless propagation environment. That is called the rank of the channel matrix. I think that's not relevant for this discussion here. Okay, so now what we have just seen in that illustration is the case when you have 4 antennas, right? So why stop with 4? You can keep increasing the number of antennas, and this is exactly what 5G has done, where the number of antennas you might have on a cell tower is all the way up to 64 or 128, right? Then you can see that you can generate very narrow different beams to many mobile devices, all right? Okay, so then that is 5G, right? Now what happens in the next generation, right? So what is going to happen is that this MIMO is going to be equipped with even more number of antennas, leading to what is known as ultra massive MIMO, right? So it's just a hardware problem now, right? You just want to have larger and larger number of antennas, which means you can generate more and more beams which are very pointed, right? So therefore, the obvious solution to meet the 6G requirement is just to have more number of antennas, right? The question is, how are you going to deploy these antennas, right? So you can have one cell tower with many antennas, that is what is called this XL MIMO, that is extra large MIMO, or you keep the antennas, the array size same, maybe keep the antenna elements closer to each other, which is what is we are going to look at is called a continuous aperture MIMO, or you keep the antennas separated and all over the network, that is called a self-free massive MIMO. Okay, so we are just going to see these different versions of ultra massive MIMO systems that we foresee in 6G networks. Okay, so let me briefly walk you through all of this, starting with self-free massive MIMO. The idea is the following. So the current networks work as follows. You have the cell towers, which are separated and they are distributed in the network area, right? Any geographical area, you are going to see several cell towers. And your mobile phone connects to the nearest cell tower, correct? And so the sort of illustration here is sort of pointing out that there are these cell boundaries beyond which the mobile phone has to switch over to the adjacent cell tower, right? So that is what is popularly known as the handover, right? You might also experience that when you move in a car, your call might get dropped, right? Because the handover failure can happen when your connection is switched from one cell tower to the another. Okay. Now, a vision for future is the following. You get rid of these cell boundaries altogether, right? So how do you do that? Okay, so you have the transmitters as before. It's just that you don't let a device connect to only one transmitter. You let it connect to every transmitter in the network, right? So all of these cell towers, which are shown by these small access points now in this drawing, are serving or are connecting to every mobile phone in the network area, right? So this is slightly an aggressive sort of a approach, right? So instead of just letting a mobile phone connect to one cell tower, now you are letting it connect to every cell tower in the nearby areas, right? So which means that there is no longer this concept of cell boundary, right? So there is no switch over of this connection because everyone is serving everyone, right? And also you are able to see that you can basically get significantly better performance by doing this, right? A device is connected to at least one device transmitter all the time, right? Now, in fact, you can show that the performance of this cell-free network is going to be considerably better. What is plotted is not very important. I'll just tell you how to read this figure. So on the x-axis here, this is the number of bits that you can transmit or serve per second per hertz, right? So every unit of the bandwidth, every unit time, how many bits are you able to communicate to a mobile phone from a cell tower? And what this result is saying is that if you look at this y-axis, that is 0.1, and for this black curve, the corresponding x-coordinate is somewhere around 1 bit per second per hertz. And for this red curve, that is going to be 6, right? So that is, this red is for this cell-free network, and this black is for the conventional or the existing networks. And what this means is that cell-free is going to give you 6 times better performance for 90% of the mobile phones. Okay, so only less than 10% of the mobile phones is going to have that much of a less of a gain, but at least 90% of the mobile phones are going to experience 6 times better data rate. Okay, so that's a considerable gain in the throughput is possible, right? So, but despite this very nice idea, realizing this in practice involves a lot of challenges. One is what is called the front haul challenge, because now when you have multiple transmitters getting signal from all the mobile phones, that has to be taken to some centralized server where all mobile phone signals are processed to recover the data, right? So therefore, this some connectivity from the cell tower to some core network has to be there, which is what is called a front haul. And there is going to be a lot of signals running through those links, and that is a very costly thing to deploy as well. So front haul, which is the connectivity from this transmitter back to some central location, is costly, which is not needed in conventional networks. And also you need tight synchronization of these signals here. All these access points have to be tightly synchronized, and that is needed because something called coherent combining, because you want the signals from a mobile phone received at different access points to be processed coherently. Okay, and also you are looking at a network where you deploy many of these transmitters here. So this idea gives you gains when you have many transmitters, small transmitters deployed all over the network area. So which means you need hundreds of small transmitters, which is again a hardware or a deployment cost issue. And all of this put together, this front haul along with the requiring many transmitters means deployment cost is also going to be high, right? Now, some of the research that I've been pursuing over the past few years has been to address these practical challenges associated with cell-free network, how to make it more practically realizable. And one idea is the following, that, okay, in this aggressive cell-free network, you allow a mobile phone to be connected to every transmitter in the network area. That is unnecessary. You can let it connect to only a small subset of the access point, right? So the mobile phone here would be served by the nearby access point or the cell towers rather than all the cell towers in the region, right? So that's a natural thing to look forward to. And what we can show is that when you have this dotted line is the case when you have only a small subset of these cell towers are connecting to a user, you can see that the loss is negligible, right? So you mostly, solid is the case of all transmitters connecting to a cell phone. But when you let only the small, maybe 30 of these 100 transmitters connect, that's a very small fraction, you can still get most of the gains here, right? So it's a simple way to realize these benefits without uh, overloading the front hole, right? The other issue is some synchronization issue. What we have also seen is that by letting the mobile phone connect to only a few of these access point rather than all the access points, you can actually reduce the delay here, and there is an optimal number of access points that should serve a UE at which you get the minimum delay. Okay, so I'll skip the details. You do some kind of latency analysis to figure out what is that optimal number of access points that should connect to a user. Right. So the other thing that we can try for is some cost-efficient self-free massive MIMO. Here the idea is that it's sort of like a hybrid of the two, right? You don't let the you don't let your cellular sort of architecture, but you don't remove the cellular architecture altogether, but you have a limited radius over which you deploy the access point, right? Instead of deploying them everywhere, you limit it to a small regions within the cell. So there are again going to be cell boundaries will be there, but also some access points distributed within that or in a small radius, right? So what we can also see is that for such sort of a hybrid of this cellular cell-free architecture, you can get better cost per GB. That is how many or how much dollars are needed in transferring per GB of data through this network. And what we have through some analysis we have seen is that there is actually a radius below which the cell-free architecture, that is the distributed deployment of this access point, is cost effective, right? So as you spread out these access points more and more, your cost is going to go up, but your performance is not going to scale up significantly. But then there is a nice optimal point at which you spread them just sufficiently enough so that cost-wise you are better, but without hurting too much on the data rate. Okay, so basically you can do this sort of network optimization, how to deploy these access points and so on. All right, so that is the idea of self-free massive MIMO. Maybe I'll just quickly introduce the related ideas. The other vision for deployment of large number of antennas is to move to something called a continuous antenna aperture, right? So currently what we are all talking about is we keep these many antenna elements. These are discrete elements, right? And you keep increasing their number, possibly by packing them close to each other. But then a limiting scenario of this is to have a sort of a continuous surface here, right? And this continuous surface can generate beams which are very finely controlled, and there is no issue of grating lobes or side lobes, right? But clearly this is not something that we can realize in practice, and always we are going to have this sort of a discrete architecture. But the idea is that the gains or the performance advantages of this continuous surface can be approximated or approached using a discrete array, but with elements placed very close to each other. Okay, so effectively you keep the antenna elements closer than the typical lambda by 2 spacing, that is half wavelength spacing, right? And the gain comes from this simple scenario, right? This is the intuition that you can have, right? So suppose you have an antenna array of size 5 lambda, 5 times wavelength is the length of the array that you have. And you can keep this you can vary the number of elements. In doing so, since the length is fixed, you reduce the spacing, right? So if you deploy 20 antenna elements, then elements have to be spaced lambda by 4 apart. But if you are only having 10 elements, you can keep them lambda by 2 apart. And if you have 5 elements, you can keep them lambda apart and so on, right? Now, by reducing the spacing and then thereby deploying more antennas, what you can show is that the beamforming gain increases. So this, if you generate a beam using this fixed array size of 5 lambda, when you have more antennas, you get more focusing, right? So more of this energy is focused here. That is what is this blue curve shows, right? And also you can see that basically there are no issues of side lobes, right? Not side lobes, grating lobes, right? You can see that when there is delta equal to lambda, there are going to be additional grating lobes are going to be there, right? That can also be avoided when you have finer spacing, right? So the advantage is that you have more antennas, but keep them closer to each other so that the overall size of the antenna array does not increase, right? And this has already also been shown in some prototypes that by keeping them very close to each other, you can create a sort of a phase profile on the surface so that the beam is generated appropriately in the direction of interest. Okay, so this surface here is fed with some reference wave, and because of the phase shift or the elements kept closer to each other having different phases, these each emitted radiation from each element would combine coherently in a particular direction of interest, leading to some beam focus to the direction that we want. Okay, but the idea is that this is also possible using what are known as metamaterials. Okay, right now one of the studies that we have carried out shows that there is again an optimal element spacing beyond which the gains are not possible. The reason is mutual coupling, right? When you keep antennas closer to each other, they start to have mutual coupling, right? The inductive coupling between the two, leading to some kind of performance loss. So as you keep them closer and closer, these coupling effects start dominating, and therefore your throughput basically start going down, right? So what it again means is that just by packing more antennas, you are not really gaining, right? There is an optimal element spacing beyond which more antennas start hurting you. Okay, so all of this means that this you also need to account for these electromagnetic effects rather than just the communication picture, and that is why often full wave analysis is needed to account for some of these electromagnetic effects and not just the wireless communication side of things. Okay, so let me also briefly touch upon the other direction in which this MIMO technology is being is expected to grow, and that is what is called XL MIMO. And a conceptual picture of that is shown here. The idea is that you might deploy your antenna array on the face of a skyscraper here, right? So the typical deployment of a 5G cell tower is on the rooftop. You might see these antenna arrays, right? But in the future, the entire face of the building may be used as an antenna array, right? You might have these small antennas placed on the full face of the array, right? Which means this is a physically large array, right? The entire face of this building might be covered with an antenna array, right? Now, when you have that physically large array, you start getting new electromagnetic effects, which are called near field propagation effects, right? And that is what is shown here when you are basically having a moderate size array and the mobile phone is far away from this array of antennas. What it experiences is a planar wavefront, but when the mobile phone moves closer to this similar sized antenna array, it starts seeing spherical wavefront, right? So ideally there is a curvature for the wavefront, but since the blue user is far away from this cell tower, right, it is seeing only a planar wavefront, but with the user closer to the cell tower, it might see this spherical wavefront, right? And in fact, the distance over which the mobile phone sees a spherical wavefront is specified by the Fraunhofer distance, that is 2d squared by lambda, where d is the array aperture. And when you have these physically large arrays, this Fraunhofer distance increases. For example, if a network operating at 3.5 gigahertz with a 2 meter cross 2 meter antenna array, it is somewhere around 200 meters, right? So that is a typical distance that you might have between a cell tower and your mobile phone, right? So you start seeing these spherical wavefront or near field propagation effects as the antenna array grows, right? Now, what's the advantage of having this? So this is sort of like having a torchlight versus a lens here, right? So in this illustration on the right, what I am seeing is showing a scenario where if you have an array of antenna generating a beam that is focusing of this energy in this particular diagonal direction here, as you keep increasing the number of antennas from 65 to 129, you can see that the beam is pointing more and more in this diagonal direction, but the width of this beam keep reducing. But at some point, say 257 or onwards, you can see that there is a focusing effect, right? So the beam is no longer over this entire diagonal direction. It is exactly localized to this particular range as well, right? So from moving from angle to range, right? You can focus your energy using a large array at a particular point, right? Not just a particular direction, right? The earlier beamforming example that I was showing, you're able to steer the beam in a particular angle, but with a large array, you can also focus it to a particular point, right? So this is called a beam focusing. And that's a big advantage because you are not wasting the energy anymore. Your energy is focused. Imagine that you have a lens which is able to focus the light in a similar manner. You have a large array which is using this spherical wavefront. It can focus the energy to a particular point, precisely to the location of the mobile phone. Okay, so just to conclude this or summarize this discussion on MIMO, we are going to have this massive number of antennas. The way they are deployed would be different. If they are spread out in the network area, you might see some version of cell-free massive MIMO, which is mostly being considered for hotspot, that is in some multiplex buildings, stadiums where you see a lot of people gathered, right? That locations where high data rate is needed, you see this sort of deployment. And then this sort of continuous aperture antennas and large antenna size, large aperture antennas are also some of the other ideas being explored. Okay. So let me just take if you have any questions here, I'll take that. Okay, so in the maybe in the okay, so let me then move to the other idea, that is reconfigurable intelligent surfaces. Okay, so this is the other direction that is being explored for 6G, right? So I mentioned in the beginning that ubiquitous coverage, that is you don't want any coverage issue anywhere in the network. And that is a very difficult problem to solve, correct? So imagine this scenario here. You have a cell tower on the top of this building. Your 5G base station is deployed here. And if your mobile phone, that is, if you are this yellow mobile phone user, you are happy, right? You have a line of sight to this cell tower. You get strong signal, right? But for this blue mobile phone here, it's an unfortunate mobile user, right? So its line of sight path to this cell tower is obstructed by this building here, and it is possibly getting a very weak signal because of that, or no signal at all, and it may not be able to get any communication going, right? Now, if you think about this, there could be another scattering body or some building here to which the EM signal is still going and it is getting scattered, right? And or reflected, and some of it is going this way here, right? So clearly you cannot facilitate a line of sight communication to the blue mobile phone here, but at least can you get a reflected signal from another building to come to this mobile phone, right? That would possibly help this mobile phone to at least get some voice call going, right? Now the problem is that this reflection follows Snell's law, and it is just going to, incident angle is going to be equal to the, or as per the Snell's law, it's going to be how the reflected angle is going to be. But you might want somehow to adjust the reflected signal to go in the direction of this mobile phone, correct? So that is the fundamental question here. Is there a way to steer the reflected signal, that is this blue signal, to the direction of this mobile phone instead of going in some arbitrary direction, right? So here we want to engineer the surface, the environment here, right? So till now, all our communication problems have been about transmitter, what does it do? Receiver, what does it do? The propagation environment is largely thought of something that you cannot control, right? Now we are asking the question, even in this propagation environment, can we do something to ensure that this reflected signal, instead of going in this direction, can it be steered in the direction of the mobile phone? Okay. So this is fundamentally where reconfigurable intelligent surfaces come in. Now, if you just put a metallic plate there on the face of this building here, that's going to act as a mirror. But then you know that for a perfect metallic conductor, the reflected signal is going to be just the opposite of the incident angle, right? So, but what you want is something to be steered in this red direction and not in this reflecting direction here, right? So a perfect metallic conductor is not going to do this for you, right? So that's again what is shown in this figure here. So if the incident angle is pi by 6, the reflected angle is going to be minus pi by 6, right? So we need something else. We need something that is steerable or controllable, and that is where reconfigurable intelligent surfaces come in. So imagine you have, instead of this sort of a perfect metallic conductor, you replace it with some kind of discrete surface as shown here. But then what is specific about this surface is that each element of this surface, you can adjust the phase of the reflected signal. Okay, suppose that is possible. So that is what is shown in this heat bar here. So the different elements, that is these small squares in this surface, they are all configured with different phase values, right? So what that means is that each element is going to reflect the incident signal, but with a phase shift given by this color code here, right? Now, if you configure these elements with appropriate phases, you can ensure that the reflected signal from all these individual elements constructively combine in this desired direction that you want. Okay, so the problem of steering the beam to the direction of interest boils down to a surface where you can control the phase profile, right? You make it with discrete elements, but each element, the phase value should be configurable. Okay. Now that is, such a surface is called a reconfigurable intelligent surface. You have these small atoms here. Each of them has a configurable phase, introduces a adjustable phase for the reflected wave. Okay. So if you zoom into a panel here, such a reconfigurable intelligent panel, each meta atom, it is going to be a basic unit is going to be there. And each of them is going to have something called a varactor diode, which is the controlled capacitance, right? The capacitance of this can be controlled by bias, right? And the capacitance controlled by this bias voltage determines what is going to be the phase shift introduced by this element here, right? So by adjusting the bias of this meta atom, you can configure the phase change introduced by each meta atom. And once you have an array of such meta atoms, you have a reconfigurable intelligent surface, right? So that serves the purpose, and the sort of the reflection coefficient or the phase change introduced is going to be determined by the surface impedance, and that you can configure or figure out what is the appropriate bias voltage needed. And this is one such surface that we fabricated at IIT Palakkad using my collaborator Dr. Sukomal De. And this is an 8x8 array with the 64 elements, right? And each of them has a varactor diode that you can use to adjust the phase value. And using this, 8x8 array of reconfigurable intelligent surface, we carried out experiments. So you have this horn antennas, one transmitting and one receiving, and you have some SDRs for generating the communication signals to be fed to these antennas, and these are getting reflected by this RIS back to the receive antenna. So what we have seen is that if you just put a metallic plate here, you get this blue is the signal that is being sent and red is the received signal. You can see that there is a significant attenuation for the received signal. But with if you replace this metallic plate with an RIS as shown in this figure, you get some 10 dB improvement, right? So the received signal strength increases by 10 times by having an intelligent surface here as opposed to a plain metallic surface. Okay, so but in general, there's a communication strategy. Now, for going back to that earlier problem, for that blue receiver who had an obstructed line of sight to the transmitter, you put this sort of a adjustable mirror on the face of this building here, so that you can steer the reflected signal in the direction of the receiver. All right. Okay, but in practice, this is not so obvious as what I have just mentioned. The reason being that the transmitter does not know the angular location of the receiver, correct? Then the difficulty is if you do not know where you want the reflected beam to go, you cannot configure the phase profile of this surface here, right? Then how do you figure out the direction in which the reflected signal to be steered? That is not a obvious thing to do, but there are ways in which we can do. One simple option is that we try out different phase profiles and see which one works best. Okay, that is one such protocol is what is shown here. So you configure the surface for different beams, right? You first generate this blue, then yellow, then green, red, purple, and so on, and try out which one gives you a strong signal to the mobile phone, and use that beam or that corresponding phase profile. Okay. Okay, so this is one of the analysis that we have did, that okay, just by equipping with many elements alone is not sufficient. You need some kind of diversity also. I'll skip the details. Okay. So to summarize this RIS discussion, and like I mentioned in the beginning, you start controlling the radio environment, right? This has not been tried before, right? But then this also means that you have to introduce this sort of mirrors, controllable mirrors in the propagation environment, and these are smart devices. The advantage is that these are very low cost, and they are just passive devices. They just reflect the signal. So the only the varactor bias voltage needs to be provided. So the power consumption of these surfaces are very, very low. So this is a very low cost, low power alternative. So you can deploy them anywhere in the network area, and this sort of avoids this issue of coverage holes, right? So if you happen to be in a place with no cellular coverage, you can have one such surface deployed to help improve the network coverage, right? But there are also practical issues that what happens if you happen to be on the other side of such a surface. There is the shadow region of, I mean, this surface itself can create shadow regions. And also the actual performance is yet to be verified in the network, right? But this is already commercial prototypes are available, and this is one such from CTE, that is a Chinese company that manufactures the radio equipment. Okay, so putting everything together, we saw that 6G requires a lot of network requirements. The capabilities have to be significantly better. And largely all those requirements, at least the throughput requirements, are going to be met by more spectrum, right? So currently newer spectrum is being made available, something called midband. That basically something from 6 gigahertz to 15 gigahertz that has not been used before, that is being made available. And particularly on the other side, you have MIMO improvements through more antennas. You also have RIS to control the propagation environment, right? So in a nutshell, the key benefits rate gains are going to come through advanced MIMO and programmable environments, all of which are exploiting the spatial dimension, right? You have this space, right? Spatial aspect is being leveraged to improve the throughput. Okay. With that, I'll stop and I'll be happy to take questions. Thank you.
Sir, I have a question.
Yes, yes, please.
Yeah. Good morning, everyone. I was listening to an amazing class. In fact, RF is a gray area for me when studying and even now. But you throw some light on that. That is really fantastic. And this is an area which is very interesting. All right. My question is very simple, sir. What are the challenges we have faced or we may face while implementation?
Yeah, so that is yes. So a lot of hardware issues. Okay, I mean, in fact, we are starting to push the limits of hardware here. I mean, till now, communication has mostly been a algorithm or a signal processing problem, and now even some of the issues that I've mentioned here, right? So these latest technologies are pushing the hardware limit. One, the compute is seriously becoming a limitation here because the sort of physical layer algorithms, right? When you say more bandwidth, right? So the signal has to be sampled correspondingly at a higher rate, and all of this has to be all that equalization. Basically, all the associated signal processing needs to be handled at a much higher rate. So the compute itself is a big hardware challenge, right? That is why we need dedicated hardware to accelerate. Hardware accelerators are needed to do this compute side of things. And also the RF side also, we have started, I mean, from a communication person to an RF person, right? So we basically work in two different directions. And now these new technologies are basically bringing in this RF side of things, this electromagnetic side of things, is one of which I pointed out, this mutual coupling, which oftentimes communication engineers neglect, assuming that there is some lambda by 2 spacing between the elements. We don't worry about such aspects, right? But these factors are also start to come in, right? So in a nutshell, yes, this communication technology is not a standalone thing. It is driven by RF improvements, all these power amplifier, low noise amplifier, mixer, all of this. New spectrum means new challenges, right? When you go to terahertz, the entire sort of hardware needs to be redesigned. So there is RF challenges. Also, digital baseband, the digital hardware which does all this processing also needs to be correspondingly better. Then only it can do all this fast compute. And lastly, we also need the algorithm side. So all of these go in hand, and with all of them only we'll be able to get better.
Yeah, thank you so much, sir. Can I go for one more, sir? Thank you so much, sir. Can you hear me?
Yes, I can hear you.
Yeah, can I go for one more?
Please.
Yes, sir. What are the expected health issues with respect to the radiation? This may be using a particular, another kind of frequency or something like that.
Yeah.
And the transmission is different, everything is different.
Yeah.
So what are the expected health issues with this?
Yeah, I think I'm not an expert to comment on that, but the one thing with all this cellular radiation, correct? These are non-ionizing radiation, right? Unlike X-rays or gamma rays, right? Which are much shorter wavelength, right? So we are talking about centimeter level wavelength, right? Which are very much non-ionizing radiation. So as such, it's not clear if there are any health concerns associated with these radiations, prolonged exposure to this radiation. But this is, I mean, my understanding is there's no conclusive answer yet. There are parties raising concerns, but these are again not verified. And also it's hard to establish, right? Unlike ionizing radiations where you might see some immediate issues, right? But like prolonged exposure, what could be some long-term health issues? That's not yet clear. So yeah, I think the short answer is that there is it's not yet established that there are health issues associated with it, but still needs to be studied or explored to see if any long-term health concerns are to be addressed.
Yeah, thank you so much, sir. Thank you.
Thank you.
Thank you very much, Oben sir. Participants can share the questions in the chat box or can raise the hands using raise hand button. So we will unmute you. I think we already have one question in the chat box, sir.
Yeah, yes, let me check. Okay. Okay, sir, from a research perspective, which area 6G currently offers most promising opportunity for postgraduate students and young researchers? Yeah, so 6G is a very vast, right? In fact, communication, right? Not just 6G or any cellular network communication. It's a vast area of research. You can do this wired network or core network, which is all the backend processing, which does a lot of network slicing, software defined networking, all of that, right? So if you are from CS background or from networking background, you can do research there. And if you are like a communication or a signal processing EC person, right, you can do a lot of signal processing challenges are still to be addressed, right? So there's a broad spectrum of research problems to address, starting from signal processing, looking at the communication protocols, how to improve them, both on the RF side as well as the baseband side. Some of the very recent exciting areas is one that is clearly AI. So there is a large push towards AI. So that is, instead of having these hand-designed algorithms or protocols making decisions in the network, you let AI agents do make that for you. And the other very active area recently is ISAC. That is, you want the network to function as a radar as well. That is sensing and communication, correct? You don't, the current existing networks are only for communication. But if you want to bring in that radar capability to the network, that you also want some velocity or target position also to be estimated using these communication signals. It's a hard problem, and a lot of research is being done. So the current strong or very active areas of research are this ISAC, that is integrated sensing and communication, and AI for radio access network. Yeah.
Sir, we have one more question from participant. We already unmuted. Ms. Rashmi, ma'am, you
Yeah. Sir, can you hear me?
Yes, I can hear you.
Okay. Thank you for the informative session, sir. I have a doubt. You said for configuring an RIS, we use a repeated pilot transmission and we choose the best signal or the strongest signal. So my doubt is, so in this case, we don't need a channel state information.
Yeah, I think the channel state information here is sort of like the SNR measurements. So although I didn't spend much time here, so the I have shown one equation also here. Ideally, this is the correct way to configure the RIS. So what this equation is saying is the following: the signal, if there is a signal arriving via line of sight, possibly that is attenuated, but there could still be some signal arriving directly from the transmitter. And there could be a signal reflected by this surface here, right? And what we want is that these two signals to arrive in phase so that they should constructively interfere upon reaching the receiver. That is effectively what this equation is telling you. So each element should introduce a phase shift such that the direct signal and the signal reflected by that element combine coherently at the, or combine constructively at the receiver. Okay, so this is the correct or the ideal implementation that we want. And this clearly requires channel state information, right? So if you, basically the other point here is that RIS is a passive entity, correct? So that it cannot make decisions on its own. So in a practical deployment, it is the cell tower that is going to tell the RIS configure these elements with these phase values, and it will adjust the phase profile here. Okay, so the intelligence is everything is in the transmitter, and it is telling the RIS, okay, use this phase profile, right? So for the transmitter to make that decision, it needs to know this channel state information, right? What are these gains directly to the receiver? What happens? What are the gains on the reflected path and so on? So channel state information is clearly needed. But in practice, when you have hundreds or thousands of array elements, this is a very difficult thing to realize in practice. So a simpler and more practical solution is to have fewer options, right? That, okay, you have a discrete set of beams, and the naive thing would be to try out these different beams and then identify the best one. Okay, so here, therefore, you need a reverse communication also, not from cell tower to the mobile phone, but also from mobile phone to the cell tower. And what happens is that this mobile phone, like any mobile phone, even our current 5G phones, they send something called pilot signals, and the cell tower can basically listen to the strength of this pilot signal, right? While trying out different beams here, that is the different phase profiles for this RIS surface, and whichever phase profile gives you the strongest signal at the cell tower for the pilot sent by the mobile phone, that is the phase profile that you should use. Or the base station tells the RIS, okay, choose this profile, and that, since that is the one that gives you the strong signal. Okay, so in a sense, yes, here again CSI is needed. It's just that it's a lot more codes, right? You only need the signal or the RSRP, but not the actual complex channel gain, right? So this is the ideal scenario. If you know the complex channel gain, transmitter can immediately tell which phase profile to use. When that has to be practically acquired, the simpler scenario would be to try out a few beams and look at the RSRP, received signal strength, for each of those beams, and pick the one with the strongest signal.
Oh, okay, sir. So we need at least a weak LOS here, right?
Yeah, I think here we don't insist on a weak LOS because all we are measuring here, I mean, there could also be an LOS component, but all we are insisting here is that LOS plus the reflected path, what is the net received signal strength for different patterns that we try.
So my doubt is, if the LOS path is completely broken or obstructed, can we use the same idea with the reflected path alone?
Yes, because so in this illustration, at least I am not drawing a signal going directly to this transmitter here, right? This cell tower here. So the signal is going to the RIS. It is getting reflected and reaching the cell tower here, right? So you try out different phase profiles while this reflected signal reaches the cell tower, right? And one that gives you the strongest signal is the one that you should use.
Okay, sir. Thank you so much.
Yeah.
Thank you, Jobin sir, and thank you for those excellent questions from the participants. Thank you for of Electronics and Communication Engineering of Jyoti Engineering College, and on behalf of all our participants, I extend our heartfelt gratitude to Dr. Jobin sir for this truly enriching session. This was a technically outstanding session, sir. Your mastery of massive MIMO and reconfigurable intelligent surfaces, and the way you connected complex mathematical models to real-world 6G deployment scenarios gave our participants a research-grade understanding of two technologies that will define the next era of wireless networks. Being an IIT Palakkad faculty and a proud product of CET and Indian Institute of Science, your work is an inspiration closer to home for many of our participants. We wish, sir, the very best in all future endeavors, and we hope to have the privilege of your presence and okay, we are going for a short break. The next session will begin at 1 p.m. Please be logged before 1 p.m. We are privileged to have Dr. Anand A. HOD, Department of ECE, IIIT Kottayam, who will be presenting on reconfigurable intelligent surfaces assisted communication. Hope you all enjoy that. Thank you. Thank you all.
Okay. Thank you.
Jobin sir, there is one more question in the chat box. If you have time, can you just...
Yes. I don't mind. Okay, can you explain the advantages of... okay, so can you explain, is that the question that can you explain the advantages of active IRS like graphene-based IRS elements over passive or a hybrid is preferred? Yeah, I think one of the challenges with the passive RIS is that there is some kind of multiplicative attenuation effect. I mean, any reflecting body has this problem. This is also why radar systems, in fact, use very high power, because the signal has to hit the target and echo signal has to reach back to the transmitter, right? So similar way, whenever there is some kind of reflection sort of an effect is happening, there is going to be some multiplicative attenuation effect is going to happen, and that is a key limitation of this sort of a passive systems. Okay, so and that is also the reason why it has been suggested that when you have this sort of reflecting surfaces, either they will be kept close to the mobile phone or they may be deployed close to the cell tower, right? So that you reduce the distance either from the transmitter to the reflecting surface or from the reflecting surface to the mobile phone. Okay, so and one alternative to this is active IRS, where the IRS is not just going to introduce a phase shift, but it can also amplify signal to some extent. Yes, that is alternative. Now the question is explain the advantages of active IRS. Clearly, signal strength is going to be so much better because the IRS is no longer a passive device. It has some power amplifier built into it, so it can actually amplify the radio signal and retransmit. Now, the difficulty or the concern there, or one of the practical challenge there is that IRS is popular mostly because that's a passive device, right? So the power consumption is very low cost device. But if you start having this sort of power amplifiers built into these devices, one, power consumption significantly increases, and also you need to have dedicated power supply and associated circuitry, right? So it's no longer a passive device anymore. So cost and hardware wise also it's difficult or different, and therefore although there are clear advantages, there are these challenges also there, right? It's no longer a passive device, it's an active device with significant power consumption. The other concern also is that there is a competing technology called the wireless relay, right? So some of you might have already this RF or this Wi-Fi extender at home, right? It's just some small device, you plug it in and then it extends your Wi-Fi network coverage, right? So again, that is sort of like an amplifier and forward relay, which just amplifies the RF signal and retransmits, right? So once you get into this active behavior for an IRS or an RIS, you start competing with the wireless relay technology, right? Which is again an active device. So yes, there has been cases where it's also shown that there are some benefits compared to, but there, once you make this RIS active, the clear advantages over wireless relays are not very evident anymore. So yes, so the active IRS is definitely better compared to a passive IRS, but then this associated power consumption, it's no longer a passive device. High power consumption is going to be there. I hope that answers the question.
Thank
Yes,
you,
sir.
sir. Thank you very much for answering one more question.